Today I am going to talk about silicon carbide based MOSFETs. In the previous video I have discussed about WBG devices, gallium nitride based devices. So here I am going to talk a little bit more about how to use these devices in our power electronic system designs. So in the last video we have seen that these devices are ultra fast, maybe 10 times faster than commercially available MOSFETs. Now the silicon based MOSFETs are available. So what are the challenges when you are trying to use these devices? So let us see one by one. First let us compare silicon carbide based device and silicon MOSFETs. So we will compare both and then we will compare the critical parameters of two devices. So the key is coming up in manufacturing these WBG devices. They are going to come up with gallium nitride device also, and then silicon carbide devices also. They are offering MOSFETs up to a rating of 900 volt and I think 26 ampere or something like in that range. So this is the part number of silicon carbide based MOSFET. So they are giving a rating up to 35 amperes at 25 degrees centigrade. Drain to source voltage is 900 volt, and then the drain current is 35 amperes at 25 degrees centigrade. So this 35 ampere is a meaningless parameter because when we pass current through a device or when draw current through them or when we control the current, the device will heat up and then temperature will go beyond 25 degrees centigrade. So we should look up at the parameter current rating at 100 degrees centigrade. So you take it as a device rating, not 35 ampere as the device rating. So you should know how to read the data sheet properly. So this is the package. Package is a SMD package. You cannot mount any heat sink on it. You have to give a heat sink in the PCB track only. You have to give a very large copper area so that heat will be dissipated. This may be one disadvantage due to maybe this package. This has I think 7 pins. First pin is the gate. Second pin is the pin used for gate driving. It also is a source, and the other rest of the pins are source, and the tab is the drive. So you have to dissipate the power through the tab using PCB traces as PCB area, copper area. So how much heat you can dissipate in this method is a challenge for this type of devices. So maybe you have to fix a heat sink on top of the copper surface of the PCB. Maybe you have to try that, whether that works effectively, or you can try while making a PCB and other things. This is the challenge. And then you are given that symbol as given. There is one more pin. Generally MOSFETs are 3 pins. 3 gate, drain and source. You got a driver source. So the source pin is duplicated so that you can easy to drive. So this is silicon carbide device ratings. Drain to source voltage 900 voltage, which we have already seen. Gate to source voltage is minus 18 to plus 19. So this is one negative point with respect to device because this needs around plus 18 volts and minus 8 volt to drive the gate. It's something like IGBT. IGBT also needs negative voltage to put it off. Similarly, this also needs some negative voltage. Continuous drain current is 25 ampere. I think 35 ampere at 25 degrees centigrade and 22 amperes at 100 degrees centigrade. Pulsed drain current it is 90 amperes. That is a very short duration rating is 90 amperes. Where 90 amperes are limited by safe operating area. So let us look at two important parameters. Input capacitance is 760 picofarad. So this is a capacitor you have to charge during switching on the MOSFET device. This capacitor will be fully charged so that the device can switch on. So you have to supply the current in a very short duration. So let us see what is the input capacitance of a silicon MOSFETs. So here input capacitance is 6800 pf. So it will take a longer time to charge a capacitor. Assume that we have same size of MOSFET driver. If you try to drive silicon MOSFET, you have to charge this 6800 pf capacitor. So it will take longer time compared to silicon carbide MOSFET where you have to charge only 760 picofarad. So almost 10 times less value. So this device can operate and the rise time can be 10 times lower. The switch on time of the device, the silicon carbide MOSFET will be 10 times lower, and so switching on losses also will be low. So switch on loss depends upon the rise time and fall time. So if the both are slow, both are very fast, and the losses during that time also will be very low. So you need not worry about whether you can go for zero current switching. So most probably that resonant converters may go out of design, because there is no need of look for current passing through the zero and then switch on the devices, because these losses are very low. So you can switch on, you can go for a hard switching. That is, when the current is not going through zero, you can switch on because the switching losses are very less. So the resonant converters may lose its charm in the coming days once these devices are coming up. So we can see that turn on delay for this silicon MOSFETs is 70 nanosecond, while turn on delay for 7 nanoseconds. So here also it is 10 order improvement in turn on delay. Turn on delay for silicon MOSFET is 70 nanoseconds, while turn on delay for silicon carbide MOSFET is 7 nanoseconds only. So there is a 10 order improvement. Now let us compare that resistance, on resistance, when the device is on, that RDS resistance, the resistance value between drain and source is 120 milliohm for silicon MOSFETs. Then let us see. The typical value for drain source resistance for silicon carbide MOSFET is around 65 milliohm, that is 50% less. So you can reduce the heat sink size by 50%. That is the meaning of this statement. Or you can draw two times more current for the same size of heat sink. You can say it in that way also. The overall product size will be becoming smaller using by these type of devices. So wherever the space constraint is there, that is wherever that this will be very much useful for military and then space research, rocket science, and everywhere you can make much smaller power supplies. Unfortunately, that junction temperature, the peak junction temperature, that temperature at which the device may fail is 150 degrees centigrade for both the devices, that is for silicon carbide as well as silicon MOSFETs. But gallium nitride device can go up to 300 degrees centigrade. So that, which is another upcoming technology, is offering a much more higher temperature range of 300 degrees centigrade compared to silicon MOSFETs or silicon carbide MOSFETs. So one of the large components in all the power devices is that magnetic components like magnetic transformers or magnetic inductors. So these round components occupy a lot of space and then and again size, and then they also create current loops of larger dimensions. So research is going on in this direction to minimize the size of these inductors. So one technology being tried is to go for 3D printed inductors and transformers. So this technology is upcoming so that size can be reduced. And then since the frequency is much higher, it is 10 times higher than the MOSFET devices, the number of turns will sort of comes down by that order. That is, if the frequency goes up by 5 times, the number of turns will come down. So people may start using the multi-layer PCBs for making transformers. Assume there are 4-layer PCB, then you can make 4 turns of a transformer. For 4 turns, it will be very large layer. So, which is a large number, because high frequency is very high. That number of turns will be in the order of in the few turns only. So in the coming days, we will have transformers of turns ratio of something similar like the primary may have 3.23 to 4 turns, and then secondary will have 1.2456 turns also. So these fractional turns also will be used to conduct exact number of exact properties of transformers. So no longer the number of turns will be in integral numbers. That number of turns will be in the fractional numbers, because the formula holds good. N1 by N2 equal to V1 by V2. So whether it can be a fraction or an integer, the formula is the same. So number of turns will be in fractions, so that we will see such transformers in the coming days. So the transformers will be fabricated in the PCB itself, and then you can drill a hole in the PCB and insert that magnetic component like a ferrite or something like that. I don't know up to what frequency the ferrite can work. So now new material may need to be developed to handle this set of high frequency switchings by silicon carbide MOSFETs or gallium nitride MOSFETs. Similarly, other components like resistors, capacitors need to be redesigned so that it will have less passive inductance, capacitance apart from what it is designed for. Another development may happen in this area is people will have to use both the sides of a PCB to mount components, okay, because higher the area held by the current loop, then higher the transmitted energy and higher the EMI RFI radiations. So keep them down, keep them inductance low. Higher the track length is higher the value of inductance. So the inductance created by tracks, PCB tracks, will create a lot of ringing in the switching waveform. So this has to be kept as low as possible. To keep as low as possible, component has to be arranged very close to each other. So to arrange a component very close to each other, one has to use two sides of the PCB. So PCBs with component mounted on both sides become normal, but it will throw a lot of challenge for the PCB design engineers. But there is no other go. If you want to keep the ringing low and keep the waveform pure so that losses are less, then you have to go for this type of design only. So let us conclude this video with this statement, and then we let us meet in another session of power electronics. Till then, see you. Tata, bye bye.